Vodcast, organized and supported by the Wireless Power Initiative. Today, we have the opportunity to talk with Professor Grant Covic about its leading wireless charging activities at the University of Auckland. Grant is a full professor with the Department of Electrical, Computer and Software Engineering at the University of Auckland, and he was a co-founder of Halo IPT that focused on electric vehicle wireless charging infrastructure. Before it was unsold, Halo IPT received the Clean Equity Monarch Award for excellence in the field of environmental engineering, and 2 New Zealand Clean Innovation Awards in the Emerging Innovator and Design and Engineering categories. Professor Covic has been awarded the New Zealand Prime Minister's Science Prize, the Vice Chancellor's Commercialization Medal, and the KiwiNet Research Commercialization Awards for his research. In 2021, he received the IEEE Power Electronics Emerging Technology Award. He is a fellow of both Engineering New Zealand and the Royal Society of New Zealand. So, welcome, Grant. As everybody knows, you are one of the world's most well-known experts in high-power electric charging innovation. And your university began research on this topic many, many years ago. So can you tell us about the main contributions to the development of this technology over the last years?
Sure. Thanks, Alessandra, and thank you very kindly for the warm introduction. I'll try and share screen to try and talk through this a little bit. So let me do that. And just bring it back. So I guess this sort of outlines a little bit of the work. Of course, everyone understands, you know, the early work in the 1900s and even before that by Houghton LeBlanc, Morris Houghton and 2 Morrises, Morris Houghton, Morris LeBlanc, and then also Tesla and Hertz and the others. So wireless power, of course, and the resonance concepts come right from the beginnings of a century ago. But largely that became an issue of how to manage the power, how to control it. And a lot of people came to the conclusion we could only do really low power, so they just put it aside. And for us, and I think, you know, this really began again, some of the ideas of this began again in the 1970s. There was some wonderful work done by, you know, I had a colleague here at the University of Auckland, but also work was being done in Santa Barbara on wireless power. But again, how to actually control this and control it with resonance really didn't come into industry until 1990. So that was work that we started again purely by accident, but that came about as there was a need for this in materials handling. And companies were saying we would like to move away from brushed systems, and we wanted to solve the problem of placing these systems into really dirty environments and ultimately into really clean environments. So that began a piece of work that we did with some industrial companies, largely working with companies like Dafuku in Japan, Vonfla, which became Conductive Vonfla. It's now then became IPT Technology, now known as NREX. But that was a driving force, I think, for not only developing the technology, but also developing some of the solutions to problems that we saw, and also that also introduced new and improved capacitors and Litz wire and the like. So over that decade, there was a huge amount of innovation because we were fortunate to be doing it at a time when the components that you needed for this technology, the switches, the ferrites, the high frequency wire, were all starting to evolve at the same time. And so that became applications with these companies. Daifuku and Conductives OnePlus started to look also at systems that could be used for AGVs and for buses at that time. And then it sort of evolved from there. All of this had to be done under resonance. So it was highly, what we call today, highly resonant. Of course, there's a lot of people who hear, or at least there's a lot of terminology that you hear about magnetic resonance, highly resonant, IPT. Essentially, they're all the same. And really all what we were trying to do was to have it resonant, have it low loss, have high Q coils, and to try and get as efficient as possible. Then I think MIT got really involved looking at doing this at distance. So while most of the systems we were looking at for this was sort of constrained within the diameter, the distances of a diameter of a coil, MIT showed that they could actually go beyond that by working at higher frequencies and with their magnetic resonance. And so then became an evolution, I think, of that sparked an evolution globally, and a lot of companies got involved in these sort of applications, and a lot of I guess academic researchers started to get really involved. And so we've seen an explosion, I think, of research, an explosion of applications, and it's been really interesting to see how that's evolving and over the last few years. So at the bottom of the slide, you can kind of see a little bit of an evolution of the systems that we've been involved in terms of our time frames. But we can talk a little bit more about that as you ask me some questions. So happy to answer a bit more.
This was a very fortunate period for the starting of this research. Also because you were able to involve a lot of industry partners. And it is curious, my curiosity is which were the main challenges that you encountered, and how the industry partners collaborate in order to solve these main challenges and to reach kind of industrial products?
Yes, it's interesting. I think this is one of those technologies where we started with purely by chance, and then we looked for industry collaborators, and the industry collaborators started working with us, saying, well, actually what we want is this, and that became a partnership of to and fro trying to solve it. I think we were lucky. We had probably a decade before anyone else got involved, or a lot of people got involved to actually work through with industry some of these problems. This is just a little example of one of those things. We started off, or at least my colleagues John Boyes and Andrew Green really began this starting of this work, and they were actually developing a power electronics converter for a completely different purpose, and it failed miserably in delivering that. But what it did do is it enabled them, with the technology of the time, with simple switches that you could buy at the time, to actually control a high frequency current in this inductive loop. And we actually were thinking, what could we do with this converter, which didn't work as the way we expected it to. And then we started to think, oh, this could be the start of doing wireless power. And we looked for collaborators. Daifuku was a company that came along and said they were actually looking for magnetic levitation or for their solutions. And they came and looked at this and thought that's probably what they were getting. But then they got something different, which is exactly what they needed. And they took it into materials handling applications. Now, the challenge that they gave us was not only to improve the efficiency of the system, because our original systems weren't very efficient and we hadn't really looked at how to improve it. We were just showing that we could do wireless power. But the other thing is they wanted multiple secondaries on one primary track. So you can imagine multiple vehicles moving along, all independently controlled. So this was our first challenge, how to actually regulate the power. And that led us to the development of decoupling controllers or shorting controllers on the secondary that would regulate the power and do it in a way where the energy, where it would do it safely. So this was the first, example of such where the switch could be turned on, it would short the output. And that was only possible because this was a current source to the load. So we could short it, or if we developed a voltage source to the load, then we could open circuit it. And we developed these power controllers to regulate the volt amps on the secondary so that the primary wouldn't be overwhelmed. But at the same time, we were also ensuring that all of the secondaries were completely independent. So a lot of the developments for track-based, I suppose, today have evolved towards other applications, which probably we'll talk about. So that was one of them. The other thing that they asked us to do was to really make long tracks. That was quite a challenge because there were a number of industrial requirements. You're not allowed in Japan, for example, to have more than 400 volts across the terminals, or 200 volts in some applications. So what we had to do if we wanted to have a long track where these vehicle systems or monorail driven systems would go along, was we had to keep compensating. So we had to work out, how do you compensate? And actually all of the terminations were problematic. So we wanted to couple in these compensation along the track length so we could get long track lengths. But the power supply that we'd started with, this one that we began with, was a load resonant supply. So the very first system we built had the other challenge that we wanted to soft switch this converter, but its frequency would vary as the load changed. And we in industry needed fixed frequency supplies. So we had to then go through a process of developing fixed frequency supplies using all sorts of developments, H bridges, using LCL or series tune systems, so that we could go to fixed frequency. And so that became a starting point for developing supplies for the Japanese industry initially. And they like to call them, this particular system looked about the size of a lunchbox, so they called it a lunchbox supply, and larger ones were called dinner boxes. So, and then we developed lots of different regulators that we could actually use on the output for getting more efficient controllers. So it became a development of working through from what was a variable frequency supply, essentially load resonant, through to a fixed frequency, long track lengths, and the like. And then I suppose, we probably don't need to go much further at that point. We can actually talk about some other questions at this point. But yeah, so that's where we began, trying to solve these problems for materials handling, really.
So this was the main challenge. And in that kind of application, the frequency was in the kilohertz range?
Yes. So we were driven originally by the demands of industry. In Japan, the radio laws are very, very strict. So we weren't allowed to go above 10 kilohertz. So we tried to go as close to it as possible. We didn't have such a restriction when we moved to Europe. So in Europe, largely the frequency was chosen what we could achieve with the capacitors or the ferrites who were available and the switches of the time. So in Europe, it largely went between 20 and 25 kilohertz, and that was simply because for the applications that we're dealing with and the switches that were available in the 90s, that was pretty much the limit that you could go with. To be honest, the capacitors were a real challenge. They started off very poor, and until you could move to ceramic capacitors, you couldn't get really stable capacitors. So the original capacitors we're working with were kind of would over time would change their value, which was one of the biggest challenges to work through for the original prototypes that we built and with industry.
So they were very important, the technologies, innovation in terms of materials, new components with higher performance. And did you see at that time already some other applications in some other industrial sectors different from the electric vehicle recharging, such as, for example, in in innovation, for example, in automation industry or material handling. These solutions were applied also in that fields.
Yes, they were. So I guess we were. I'll see if I've got a slide that can perhaps talk to that. So of course, this was the kind of where Dafuku and conductors Wampler were interested in, but there was also one of the interesting ones was companies that we talked with who were interested in roadway lighting or lighting solutions. So this is one example of that. Here you've got a request to actually place lights, which particularly in tunnels wouldn't actually go out if there was a tunnel fire, or would actually provide light on the road rather than at the time it was just purely reflective systems. But as soon as you got into a system where there's heavy rain, or you've actually got a system where there's snow, the reflections, of course, weren't able to be visible, so you lost where the road was. So they asked, could we actually provide a solution for putting it into the road? So we actually had these. We would cut a sort of a slot in the road and put a active resin intermediate. So we'd have these first resin intermediates in the road, and then they'd seal up the road, and we'd drop the lights just onto the road. So therefore, if they got knocked off at any point, you could just replace them back on. But this provided the ability for particularly in tunnels and in awkward lighting environments, to actually provide lighting for various applications that got around problems. And then, of course, as soon as you actually started to provide power, they said, "Oh, could we actually control the lights and change their color, change all sorts of applications?" So then came along communications. So there was, alongside the wireless power, became a guided wireless communication requirement, not radiated, but sort of that was utilizing the same pathway. So that was one of them. I think there was many applications at the same time, thinking about small devices like cell phones or laptops. So that was obviously an interest. Could we actually start to remove all the problem connections? So and then at the same time, there was an interest from the medical community. Could we actually provide those power into heart pumps or to other medical devices, which at the time, with the wires coming out of the body was a real issue, and still is today. So there's a lot of work that we started some early work on there, which even today is there's a lot of work going on.
Yes. In fact, my question is, all these ideas that are quite old, let's say, are still adopted in nowadays.
And I think there's a lot of research still in these fields. For example, trying to get smaller, lighter, more efficient wireless power applications for use in all of these systems is a challenge even today, and that's certainly been it keeps this field really interesting and fresh, because everyone that you're working with, or all of the companies that you work with, they all end up with an application-driven constraint, and they are asking all the time, how can we improve this? How can we make it lower cost? How can we make it smaller? How can we increase the power density? So those are all interesting challenges. How can we extend the coupling distance within our constraint? These are ongoing, evolving problems, which makes the wireless power forever interesting, I think.
And the distance, the maximum distance you reached in these applications, which was?
So we were largely focused on near field couplings. So we didn't get involved in the radiative side. This, of course, has sort of where I think many colleagues in MTT came from the radiative side back into the near field coupling. We kind of evolved the other way. Our distances largely were driven by the applications of the time. So if the original applications in materials handling, for example, they're all monorail. The original were monorail driven systems, so that the gaps were maybe 1 or 2 centimeters is what they were looking for, because they were trying to solve the problem of not having to have a brush system, which would have caused an arc or a spark or particulates, which would impact a clean room. So that all the clean rooms became completely wireless powered. They weren't really looking for high distances. When you look back at these sort of applications for electric vehicle charging, the original gaps, we would keep them small for efficiency to increase the high power. So you can see in this application here for charging, we did in 95, 96. This we actually had a lump in the road to keep the gaps small, and that was similar for the work we did with conductless fault flow. The gaps were kept small, but then of course there was the request: can we actually increase the gap? Can we remove the lumps on the ground? And so probably we're working within the coil diameter for most of our applications, or half the coil diameter, because that we got really good couplings with those. And I think it's only been recently that larger distances have been looked at, but you're always fighting the basic equations. How many volt amps are you prepared to put into a coil to overcome the low coupling? And as you go into higher power, that becomes a challenge. And at low power, maybe you can live with high volt amps, because it's you're only transferring very small amounts of power. But at higher power systems for high efficiency, what's the comfortable coupling range that you want to work within? 0.1 seems a nice level to 0.2, but
this is
0.01 becomes a challenge.
Okay. So this is a good point. And this up to now, we have mainly discussed about solutions at the industrial level related to static wireless power transfer in most of the cases. But now there is an emerging need of dynamic power transfer solutions. And can you comment on what is your view about reaching similar performance when you want to address this technology while the device is moving?
Yes, I think it comes down to a number of things as to so of course the earliest moving systems were these type of systems where really they're the predecessor of what people are trying to do now with dynamic wireless power. I'm trying to think of if I can talk a little bit. So here's kind of what people want when they go into they want to go to have a vehicle that will handle and take advantage of static wireless charging, or semi-dynamic or dynamic. So this is where the real challenges are when we're thinking about a system that might go to an automotive and take advantage of dynamic. The advantage of going dynamic, of course, is that you could lower the battery weight, and you're wanting to not carry all the energy. So if we take the standard models that we have for transportation today, we carry our fuel until the fuel runs out and the vehicle gets lighter as we run out of fuel. Ideally, with batteries, the batteries are heavy and we're carrying these heavy batteries with us. It's not ideal. If we can lower that battery weight, we can gain a lot of efficiency. And one way to do that is obviously to utilize dynamic EV charging. The challenge is to have a system, obviously the design of the magnetics needs to be such that they can take advantage of both stationary and dynamic, because it's going to need to make use of both for transportation. That dynamic system typically needs to be tolerant to movement and tolerant to the driver demands. So that's kind of at odds with the way static EV charging focuses, which is we're going to align it as best we can, and we're going to ensure that that we can get the highest efficiency. So you're always going to trade off a little bit in efficiency, not a lot, but you have to expand your magnetics to go from maybe single coil options, which are very sensitive or very directed to the alignment of where they're positioned, to multi-coil systems on the vehicle, which will actually pick up the full vector of flux, because of course flux is a vector. It has horizontal and vertical components, and what you need to do is have something on the vehicle which can pick up both elements of the vector of flux and capture it as best you can within the area of the coil, and then utilize that power effectively. So the way the systems are evolving is improved magnetics and of course improved electronics. So you've got to be able to regulate the power on the moving system. Whereas if you go to a static EV charging system, you can almost get away with just rectified system on the vehicle side, keep it nice and simple, and do all your power regulation on the ground side. And that keeps the vehicle simple and has simple coils. Once you go to something that's moving, largely what we've got to do is set the field along the road or energize it in segments under the vehicle, but the vehicle then needs to regulate it for its own needs. So you need active regulation. You need to use that active regulation in such a way as to improve the efficiency. So there's a lot of work going on both in the magnetics, there's a lot of work going on in the electronics, and there's also a lot of work going on in improving the materials again. So while we saw in the early days huge improvements by going to ferrites and litz wire, we're seeing similar improvements trying to work out today with improved capacitors, moving from utilizing ferrites to lighter weight materials like nanocrystallines, and trying to get the weight down and get the power densities up. So those are the big challenges with a dynamic system, because you don't want to carry the weight. And then if we can do that, we can reduce the battery weight of the vehicle, and it can take just enough battery for doing sort of the sort of movements around the city that it needs to, but when it goes long distance, it can take advantage of collecting power as it goes, really, and that creates a much more efficient system.
So there is the need for also sort of a creative approach to the design of the wireless link, in particular using materials with different shapes and different shapes of multi-coil systems. This will help reaching your goals. Yes, but
yeah, and I think there's the big challenges which people often don't think about, or at least many academic papers don't think about, is the fact that you don't get to architect both what's in the ground and what's on the vehicle. It may be your system is on the ground and somebody else's system is on the vehicle, and they may have a different architecture to what you thought. So interoperability is now the huge question here.
Sure.
Can we design systems which will work with other people's ideas? So therefore, it's a really important aspect of the design. If I build a system into the road, it's got to work with different vehicles of different power levels, of different heights to ground, and it's also got to be able to tolerate a different magnetic architecture. So and different regulation mechanisms. So often what you'll see in academic papers is that they propose a ground system and a vehicle system, and then there needs to be a lot of work done looking at what happens if it's not my vehicle system and somebody else's, or if I've got a vehicle system, am I tolerant to all the different types of ground systems? So this is where I think a lot of research is moving at the moment, trying to make improvements on this, trying to become more tolerant to other people's designs.
Yes, so you think there is the need for some standardized regulation so that the interoperability will be more easier to be achieved? And do you think there is some work on this so that people designing different subsystem parts can be sure that they will interact with the other subsystems? Is there any activity on this field, I guess? Yes.
Yeah, there's a huge amount of activity in standardization, largely in the automotive industry, for vehicle applications. That probably slows down and has slowed down the introduction of this for automotive. So while we saw a very quick uptake in materials handling, because it's not driven by standards, it's more driven by the regulation of making sure it doesn't interfere with nearby systems, but the actual architecture, isn't needed to be standardized. When it comes to automotive systems, standards are everything. The automotive industry does not want something on their vehicle that won't work with something else. So they're keen for interoperability, but they want everything to be standardized. So that process of standardization is incredibly important. It's not something that academics normally get involved in. It's something which we have got involved in because we could see the only way through to seeing this realized in practice is to be at the forefront of standards development. And so I think one of the things that has really helped is the standards have selected a frequency. That means there's been a lot of industry development around improving lits wire, improving the magnetics that will work at that frequency, because because the component manufacturers see that there's the potential to sell those components which will work at those frequencies appropriately. So 85 kilohertz has become the key driver for the automotive applications.
Oh, okay.
But when you start looking at other applications, there aren't standards, and there's some freedom to pick a frequency. Say for drone charging at a much higher, where you want much lighter weight systems, they could be chosen in the megahertz region, for example.
Yes.
But the challenge with standardization is you must fit within the frequency spectrum, and your harmonics have to fit within the frequency spectrum globally. So finding a frequency that's going to be appropriate and will be approved is a huge amount of effort. The car industry has been working on this to realize the frequency for EV charging for the last 2 decades, and had to work very closely with all of the ITU, with CISPA, with all the various authorities to get permission and to get allowance for this use. It's not a simple matter of saying, let's pick a different frequency. So when we come to drones or maybe bikes, electric bicycles, the question of choosing the frequency has to be very carefully taken, because there's there's some obviously open bands of frequencies which people make use of, 7 megahertz or 27 megahertz or these sorts of things they can look at, but you can't just arbitrarily pick a frequency and move out of it, because somebody will get upset. So you've got to work very carefully alongside these lines. And that's part of the standardization process. And that drives then improved solutions and magnetics that suit those frequencies.
So the megahertz range is interesting and attractive for some aspects, but what are the main limitations for when you use a lot of power, wireless power with a high density? Why the megahertz region has some limitation, in which fields?
I think megahertz range has got a lot of application for kind of systems up to about a kilowatt or so. I think when you look at drones, is an obvious you want to lighten, make the systems much more lightweight. So it seems clear to me that would be a great frequency to go into the megahertz region. When you move into some of the other applications, taking advantage of the improved power electronics, the improved magnetics, these are things which you want to do. as you know, it's a classic curve. As you move up in power, you move down in frequency, because that's where the efficiencies, you find the efficiencies. So it's very hard to push the envelope of frequency when there are constraints on the power switches and constraints on often the magnetic components, the tuning components, and the like. So of course, lots of evolution is happening in the industry in terms of different ways of getting natural resonances or controlling the resonances at higher frequencies. I think it will be difficult to move the automotive industry from the 85 kilohertz, because so much effort has really happened globally to make that happen. But I think there's so many applications that people forget all the other applications which are sitting out there, which would take great advantage from the higher frequencies. You know, the medical applications, although you have to be very careful and look at how does a particular frequency in a medical application impact the human body. You have to look at also, you know, how does it maybe interfere or not interfere with a neighboring device. So every frequency you look at its application and say, how does this fit within the environment it's operating, and will it actually interfere with something else? For example, there were frequencies we were looking at choosing for the automotive, and we chose not to use some of those frequencies because they were too close to the frequencies of the systems on the vehicle itself, like the door openers and some of the systems which are being used. So you have to really look at I guess it's living within the environment it is, but I think there's huge opportunities at the higher frequencies for many of the applications I see. And of course, once you move into an industry, you've got many applications in industry where you could take advantage of higher frequencies, I think. So I think there's a huge application range for wireless power, which we haven't tapped into yet.
Yes. So we have discussed about the different operating frequencies depending on applications, and especially depending also on power levels. And in your opinion, if we address coming back to the dynamic charging of vehicles, what is, in your opinion, the realistic highest power level that can be transferred in dynamic WPT or even in static WPT? Because now few tens of kilowatts are demonstrated, but the dream is to increase it significantly. What do you think?
So I think it depends on the application and the need, and I guess this comes down to a philosophy of what kind of power levels we do need. So there are already applications that are transferring up to megawatt wireless power. The question, and naturally the electric ferries and the like. So those sort of systems are already being developed. The question is how much power. I mean, always there's demand for more power, but as the batteries improve, the power densities improve, then the question comes down to how much do we actually need to charge for the particular application. So, and how much do we want to transfer or carry energy? So one of the questions we're looking at in terms of with colleagues who would do optimization in econometrics is what are the advantages of lightening or lowering the battery pack size, carrying less energy, being able to charge at a lower rate, or charge it at a lower power level, but fill up the battery faster if we can take advantage of dynamic while we're traveling. So that brings a lot of efficiencies, because you know the vehicle is not carrying as big a battery, and it can actually carry more passengers. This is obviously a question when we look with the aerospace industry. We don't want a lot of weight on a plane. We want to carry passengers. So what is the ultimate battery capacity for the application? So transportation has always been, let's carry the fuel. But now the question is, do we need to carry all this fuel, and what might be the best charging solution? Also, this has big implications, obviously, when it comes to automotive, is, you know, how much, how large are these charging stations going to be, and what impact will they have in terms of locating these charging stations? And if you've got 10 vehicles charging at really high power, you've got a huge, you know, power station almost at the charging station itself. So if we can lower the charging rates, if we can charge faster, then that actually is helpful, because you know, the vehicle is taking advantage. It doesn't need to carry as much energy. So the application is driving, I think, the levels of power. For automotive sort of systems, a lot of people, when they actually get an electric vehicle and they drive around town, find that they can happily charge at 3 or 8 kilowatts, and they don't really need to think about things too much for the vehicles. It's only when we actually start driving long distances we start thinking, oh, I need to stop in at a fast charger, and I'd like to charge my battery up maybe within 10 minutes or something, or 15 minutes. Then we start thinking about higher and faster charging. So I think the applications will drive the power demands. I don't think there's a limit to what we could transfer, but the application, I think, will limit us. So is there a reason to have really large power transfers? Obviously, as we move towards larger gaps, people have talked about beaming energy from space wirelessly. I mean, there's huge potential, but there's also challenges in doing that. If you can't shut the system off and detect an interference, you know, whether that's appropriate or not, that's a lot of work to be done on that. But I think the applications are certainly there for higher power. I think certainly we're seeing them in some of the industries. As I said, electric ferries is a classic one. And I think probably we can see high power demands in charging aircraft at the gates. We're seeing sort of demands for up to 200 or 350 kilowatts for charging aircraft. But these are trading off against how quickly the batteries will accept some of these charges. So the batteries are improving all the time, and it's evolving. But I don't think we're going to be limited by our capability to transfer power. I think the applications are going to tell us what we need to do.
It's very interesting, this vision, because it shows that it is not a matter of trying to design efficiently the link, but also to know how the batteries will evolve. So it is linked, and it is not expected at the first vision, but it is very interesting to see that this is related to the aspect of the batteries. In any case, in your opinion, the new vision of electric vehicle mobility is strictly related to the possibility of really implementing infrastructure, as you have shown, that allows dynamic wireless power, or do you think it is a very fundamental infrastructure that we will need in the next future to effectively exploit?
Yeah, it's an interesting question as to I think there's clear applications which take advantage of dynamic, or at least would benefit from taking advantage right today from dynamic wireless power. But then there's obviously questions about whether we need them for around town. For example, if we look at our personal vehicles driving around town, most of us would just be happy charging at home. We probably don't want to think about plugging in, particularly in cold and wet and difficult weather. So wireless charging at home would be beneficial. But not everyone has the opportunity to charge at home, so they want to charge, maybe be able to have opportunities to charge in parking buildings or on the street. But where does dynamic fit into that? Well, I think dynamic can fit into corridors, for example, for larger vehicles or for taxi lanes, or for corridors where you go from a port. There's a lot of large, medium vehicles and heavy-duty vehicles which pick up goods and move it from a port through to a loading dock, and just go backwards and forwards all day long. And they actually just want to take the goods. They don't want to be dragging batteries backwards and forwards. So you could take advantage of a dynamic system there. It's a very defined corridor, an easy application for dynamic. And I think that's where people see a good application for this. There's obviously advantages in terms of how often do we actually need to charge a vehicle if we can lower the battery weight? Then the demands on dynamic go down. So I guess I've seen some really interesting research. It shows that yes, it makes economic sense to go dynamic, but no one is ready to go dynamic yet until we have enough vehicles which says this is what we're going to work with on the vehicle. So it's a chicken and the egg between what are the evolving and improving systems going on into vehicles, and therefore what will we actually put into a roadway for dynamic. And I think there are clear corridors within every country where there's a lot of vehicle movements, where you could actually have 3 to 5% of the roads sort of servicing up to 25% of the vehicles very easily. And if they were the focus areas for dynamic, it would make a lot of sense. But you wouldn't want to put dynamic applications or dynamic systems into corridors which have very low traffic. It would be probably a poor use of the infrastructure. So it's a balancing act. How much battery do we need versus how much can we take advantage of dynamic corridors to improve this? I think the automotive one is a particularly challenging one because actually the roading is largely driven by the demands of the heavy duty vehicles. But there's a smaller number of those and a much larger number of smaller cars. But you've got to design for the largest vehicle, and that's where you've got to think about the corridors.
To choose the system. Yes. Thank you very much. Up to now, thank you. I have some last few questions concerning the technology as a whole. We have implicitly discussed a lot about inductive wireless power transfer or resonant inductive multi-coils and so on, but we know that there is also the dual possibility that is related to capacitive wireless power transfer, which is much less exploited up to now. Can you tell us why this? Because theoretically they are exactly the two ways to transfer energy, either magnetic or capacitive. But why capacitive links are still almost at the research stages and didn't have?
So I think capacitive power transfer has a lot of benefit and a lot of industry, particularly where you've got metals. And you want to take advantage of electric field. You can't get the inductive across. I mean, the classic challenge you've got with capacitive is that you're working with permittivity. The electric field is the E naught versus the U naught. So permeability enables us to actually transfer power at much lower frequencies with inductive. Whereas in capacitive, you've got to move 2 megahertz to overcome the permittivity constant, and there's about a power of 10 to the 5 difference between them. So in order to actually transfer the power, we've got to overcome that challenge. Pushes us to higher frequencies, and as soon as you push to higher frequencies, you're on the cusp of working at lower power levels, because the switches that you're trying to make use of, the componentry is trying to make use of, make it slightly more challenging. the capability to transfer power, if you do it under resonance, can be just as efficient whether you're doing capacitive power transfer or inductive power transfer. But it's much easier to transfer higher powers inductively. So because you work at lower frequencies, you're taking advantage of the switches and the components there. But I can see there's lots of applications where capacitive power transfer can be very helpful, and I think they will evolve. We've seen areas where we actually need to make use of capacitive power transfer because the metals in the application are blocking us being able to transfer inductively. So we've actually, in some applications, we've actually transferred capacitively and then turned it around and transferred inductively in another part of the same application. So I think that's a really upside of capacitive, and I don't think there's any real challenge when it comes to efficiencies or EMI that you can, so long as you can capture the fields, you can actually handle it. But where the other difficulties come into is managing the tuning or the capacitances in a capacitive power transfer system. And I think also there's always concerns around, how you manage the high voltages that you need within that electric field. So, and if you can't actually capture all of the field, then it's going to radiate. So you've got to, so you've got this where you've got the closed form fields for inductive, electric field will go until it hits another plate. So I think it's definitely an evolving field. It's clear there's been a huge amount of work being done over the last decade, which has shown that you can get really high efficient systems that could be applicable for a number of applications. I think the question is which of those applications we're going to pick, and I think there will be a number of them. But
for example,
maybe
underwater, do you think in that case perhaps we will have some advantages?
Well, I think when you actually, whenever again you can do both inductive and capacitive underwater. I think that the challenge in inductive is easy until you hit metals. So I think in applications where you've got metals and you can control the gap, capacitive could be very helpful. But I think I've seen applications where they've had them in capacitive coupling and all bars, all sorts of sort of applications like this. I think there's probably it needs some applications to come forward which we can actually apply it to. But what I've also seen is a lot of people applying capacitive to electric vehicle applications. I think that's can be a good application, but I think the automotive industry has already moved so far down the inductive route that it's probably one that's going to be difficult to challenge because the frequencies have already been chosen for power transfer. But I can see so many other applications of capacitive power transfer where it makes a lot of sense. So I think we need to start doing a lot more research with capacitive power transfer.
Thank you. And my last question is a question of your view for the future activities in industrial, both industrial and research. And we have spent a lot about batteries, inverters, and materials. In the next let's say 5 years, in your opinion, which components of a WPT system you expect will have the big performance boost using, for example, new semiconductors, new materials, and so on? Which are the most promising ones?
Yeah, so that's a really good question. And again, it's application based. But if I go to the industries I'm most familiar with, industrial and automotive, the biggest challenges in the magnetic sets, because we've got the highest loss, And so and the biggest demand is to lighten the weight. So moving towards nanocrystallines is obviously something which people are very keen to do because ferrites are bulky and weighty. It's difficult to know how to move away from lits. Lits obviously is heavy, but it's probably what we still need to make use of at the moment. Although people have looked at printed circuit board designs and getting lightweight designs. I think the switches are clearly improving hugely. That 5 or 10 years ago, industry was not really comfortable moving to silicon carbide, and then they switched and said, yes, we're now comfortable with it. And I think as we see wide bandgap devices coming on board, that's going to help us improve. But the converters are already 99% or 98% efficient. So it's really in the magnetics where we see the biggest challenge, I think. So when I look at some of the designs, it's obviously the inductors where we need to put our biggest efforts. The capacitors are pretty good. And so there's always, and alongside that, the power density is the challenge. So as we try and bring the power density within a smaller area and raise that power, now we need our colleagues in mechanical engineering to work alongside us in terms of how do we manage the thermal, how do we cool systems a lot better than what we are today, and we can push the power densities or the current densities and the magnetic field densities up higher. So and without actually sort of exciting nonlinearities and causing problems. So people show you ideal systems at ideal operations, but as soon as you push the limits, you start getting nonlinear behaviors and thermal constraints. So I think that's probably where a lot of evolving improvement is, understanding how to best design these systems.
So it will be a matter also of interdisciplinary approaches, as you said.
Yeah, I think interdisciplinary is critical right now, but for all the applications. So, and I think actually I find that really encouraging, because when you bring in somebody from mechanical engineering or civil engineering and they start bringing in their ideas, creative thought processes followed, and you start thinking, oh yeah, we could do that. Why haven't we looked at that before? And it opens up the door for new ideas. So yeah, I found that particularly rewarding, actually, working with colleagues outside of power electronics. So
a different point of view.
Different view.
Yes. Thank you very much, Professor Covic, for this very interesting and broad discussion about wireless power for automotive and other industrial applications. It was very interesting. I hope it will inspire a lot of young engineers and students. And we will discuss about these themes in the next wireless power transfer conference in Rome in June, and so perhaps people will attend. Thank you very much.
Yeah, and thank you, Alessandra, for taking the time to fire all these questions at me, and hopefully we've been able to capture some ideas. Yes. I'm sure there are many more ideas that are evolving with colleagues globally.
Yes.
So this is what's fun. In fact, I think one of the exciting things about having a conference where we bring together people from both the radiative and the coupled side is we're now seeing emerging of new ideas from that interaction. I think that the family of people working in wireless power has broadened, and it's become really interesting, that sort of interaction. That I've actually found the conference we're talking about, it's just so much more fun when you're talking outside and people are showing you their new ideas and applications. I've been fascinated by how people take this into different areas. So it's really, really interesting.
Yes. Thank you very much.